This lesson deals with Supplemental Problem 6.5. You can find this problem in the course ebook in the Chapter 6 Supplemental Problems, starting on page 5. Most speakers cannot reproduce the entire audio band from 20 Hz to 20 kHz. So we have specialized speakers. A woofer is a speaker that can reproduce tones typically in the 20 Hz to about 750 Hz range. Mid-woofers can reproduce tones typically in the 750 Hz to 6 kHz range, and tweeters can reproduce tones in the upper end of the audio band from 6K to 20K. So we need to break up the audio band into pieces and send those pieces to the speakers that can reproduce them the best. Here's a block diagram of just the left channel of a set of crossovers where I have my music coming in and I feed it to the input of 3 circuits: a low-pass filter, a wide bandpass filter, and a high-pass filter. And these are eventually connected up to the speaker. Now this low-pass filter needs to be able to pass signals below, say, 750 Hz, the frequencies that the woofer can reproduce. And the slope here, we want to be as steep as possible. So we're going to use our second order low-pass filter for getting a slope of minus 40 dB per decade. For the high-pass case, we want to pass the frequencies for the tweeter, which would be about 6 kHz or higher. And again, we want to block the frequencies below that because the speaker can't reproduce those faithfully. Then lastly, we're going to take a look at making a wide bandpass filter where I'll be able to pass the frequencies above 750 Hz all the way up to 6 kHz and send that to the mid-woofer. Now all these filters were down 3 dB at their omega naught frequency. Let's take a look at finding circuits that can do this. A speaker has an impedance that varies with frequency, and we can roughly treat it as a constant in the band of frequencies that we're going to use it. So we need a filter that would have a resistive load for its output. And we had a low-pass second-order filter in Supplemental Problem 6.3, and this will be our speaker. Likewise, in Supplemental Problem 6.4, we had a high-pass filter, which we're going to use for our crossover because it had a resistive load right here, and that's going to be our speaker. We saw in Chapter 6 on page 20 and 22 that our second-order low-pass and high-pass filters, when they had a Q0 of 0.707, down 3 dB at omega equal to omega naught. And that's exactly what we need for our high-pass and our low-pass crossover filter. As I mentioned, the impedance of a speaker varies with frequency, but we can roughly approximate an 8 ohm speaker as 8 ohms of resistance in its band of frequencies. Let's design a low-pass and a high-pass crossover filter using L's and C's that are in a practical range, say from 0.1 nanohenries to 100 millihenries, and our C's from 100 picofarads to 100 microfarads. Our specs for our low-pass crossover filter is that the value of R is 8 ohms and the value of Q0 is 0.707. Now in Supplemental Problem 6.3, we saw that Q0 was equal to R square root of C over L. We're going to set Q0 equal to 1 over square root of 2, R 8 ohms, and now we got to pick L and C. So I have one equation and 2 unknowns. I have a second equation and 2 unknowns, and then omega naught for our low-pass crossover, which is at 750 Hz. Multiply that by 2 pi, and that's going to be equal to 1 over square root of LC. Let's solve this equation for the square root of C. So bring the 8 over here, bring the square root of L over here. I have an expression for the square root of C, and I'm going to put that in for this term right here. 2 times pi times 750 is equal to 1 over the square root of L, and then the square root of C is this term over here, which is square root of L divided by 8 square root of 2. Multiply these two together, I get an L squared square root, so it's just the value of L. I'm going to bring that over here, and then divide by 2 pi 750, and then the reciprocal of this up in the numerator is 8 square root of 2. And that's 2.4 millihenries. Knowing the value of L now, I can go back and get the value of C, and probably the easiest equation is right over here. Square both sides. I'm going to get a 1 over LC, bring the C over here. Squaring this side of the equation, I get omega naught squared, which is 2 pi times 750 squared. And then the value of L, which is 2.4 millihenries. That gives me about 18.76 microfarads. These are not standard values, but let's just use these to take a look at our filters and some of our data. We'd of course round this to the nearest standard component. Here's my value of L, my value of C, and my speaker of 8 ohms. If we make the input 1 volt at angle 0, then this node voltage becomes the transfer function. So that makes the collecting lab data a lot easier. For a high-pass circuit, our specs were that R was 8 ohms and that Q0 would be 0.707. And from Supplemental Problem 6.4, we saw that Q0 was equal to R square root of C over L. I'm going to pick Q0 equal to 1 over square root of 2. And now we've got again one equation and 2 unknowns. My second equation is the value of omega naught at 6 kilohertz. Multiply that by 2 pi to get the value of omega. And that's equal to 1 over square root of LC. Let's again solve this for the square root of C. Bring the square root of L over here. Divide by 8, my value for the square root of C, and I'll plug it in over here. 2 pi times 6k is 1 over the square root of L, and then the square root of C is this term over here, which is square root of L divided by 8 square root of 2. Multiply these two together, get L squared square root, that's just the value of L. I'll bring that over here. Divide by 2 pi 6k, bring it over here, and then bring this up in the numerator as 8 square root of 2, and I get 300 microhenries. And go back to this equation and solve for the value of C by squaring both sides. Get omega naught squared, bring that over here, and bring the C over here. 1 over omega naught squared, and then L. 2 pi times 6k squared times the 300 microhenries, and I get 2.345 microfarads. My circuit now with this capacitor and this inductor and my 8 ohm speaker will give me the high pass crossover. If I again use 1 volt at angle 0 here, then this node voltage, I'll call it node voltage 3, would be my transfer function. There's V3 divided by V1 is just node voltage V3. I'm going to use that for collecting some lab data. So I take a look at the bandpass filter. We need a wide bandpass filter for the mid-woofer speaker, and the bandpass filter that we looked at in Chapter 6 is just too narrow. Go back and take a look at page 5. Let me show you a little trick. Here we have a very wide bandwidth for our bandpass filter. You could think of this as the combination of a high-pass filter and a low-pass filter. We'll take a look at using these two other filters, our low-pass and high-pass, and combine them to make this one. Take a look at this on page 8. So here's the C and L of my high-pass filter and the L and C of my low-pass filter. I'm going to pick the corner frequency for this one to be 750 Hertz and this one to be 6 kilohertz. The frequency is around 750 Hertz. This inductor will look like a short circuit and this will look like an open circuit. And I'm left with C and an L and an R in parallel. In other words, our high-pass filter. Then as the frequency increases beyond 750, this will become a short and this will become an open. And now we'll have our low-pass filter, which we're going to set at about 6 kilohertz. I take the formulas I had for the high-pass filter for my inductor and my capacitor and just use those now with a value of 750 Hertz. So I get 2.4 millihenries and 18.76 microfarads. Now let me use my low-pass equations for these two. Just putting in now a frequency of 6 kilohertz and 6 kilohertz, and I get 300 microhenries again and 2.345 microfarads. Let's take a look at what the lab data would look like for plotting the Bode plots. What's plotted here is node voltage 2 from our low-pass filter, using the exact value of the components that were shown on the previous pages. You can see here I have the low-pass function, and I'm down 3 dB at about 750 Hertz. Then my high-pass data was my node voltage V3, and you can see here that when I get to about 6 kilohertz, I'm about 3 dB down. And then as frequency goes up, I level out with a gain of 1. So I do have my high-pass and low-pass crossovers working. Let's take a look at our bandpass case next. For the schematic on page 8, the output voltage was node 5. You can see here's my data. And you can see that my gain here is a little bit more than 0 dB. I'm getting some loading effects between the two filters. And again, it's an approximation. But you can see here at about 750 Hertz, I'm down about 3 dB. And here at about 6.7 kilohertz, I'm also down about 3 dB. So close to what I was designing for, but not exactly the value because of the loading effects of the L's and C's from one section to another. What I've graphed here is everything put together. So here's a plot of the low-pass Bode plot, the high-pass Bode plot, and then the wide bandpass. And you can see that they crossed around 750 and about 6 kilohertz. So what's happening when you're listening to the music? Well, we took the music and split it up between the three filters, and now the three speakers are producing the sound. Now your ear acts as a summing circuit. So it's taking the signal from the woofer and adding it to the other signals, but these are very, very small because they're less than 0 dB. So you just hear the low frequency. Likewise, for the high frequency, you just have these very small results being produced by the two other speakers and just hearing what's coming out of the tweeter. And then for the wide bandpass, we're getting the value from that, but the other values again are much less than 0 dB, so they don't contribute very much. So your ear actually adds together those three speakers' response to put together the original signal. And this is supplemental problem 6.5.